Welcome everybody to the second hour where Salvatore will tell us about an introduction to log schemes part 1.
Thank you. Okay, so now let's see maybe some more precise definitions after this introduction. First of all, I want to start with a situation which actually motivates the theory, and that was studied before the introduction of this theory. So if X is a regular scheme and we have strict normal crossing divisors, so this means that either in the étale or the risky topology, so this means that locally X is a regular V, and if T1 Tm is a maximal regular sequence, then D is actually given by an equation of this form for some K. And in this situation, it's classical, and many of you probably know that there are many things that one can construct and call log, like differential form with log poles or regular connections with log poles along D. And in fact, this will be a motivating example of, so this divisor will induce a log structure on X, and in fact the theory takes the name from the fact that logarithmic was already used in this setting. So let me give the definition, and then I will describe the log structure associated to that. So X scheme, then a pre-log structure on X is a morphism of sheaves of monoids, and now one can give the same definition for a sheaf over the étale or the Zariski side. So we have this morphism. Here M is a sheaf of monoids on X, and OX is always considered as a sheaf of monoids with respect to the multiplication. And then a scheme equipped with a pre-log structure is called a pre-log scheme. I will actually denote it. So usually I will use this notation, so that then I will just denote the underlying scheme with X. So, but sometimes I can also switch to David notation. And now, if we have a morphism, if we have two log schemes, two pre-log schemes, then a morphism between them is the following. So we have, it's actually a couple, F underline and F theta, where this is just a morphism of the underlying schemes, and this is a morphism of sheaves of monoids. So what we can do, we have our F here, we can take the inverse image sheaf of N, which is a sheaf of Y, and now this should map it onto M, and then we require that this diagram is commutative. So here, this is the map induced by our map of schemes, and these are the two maps giving the pre-log structure on X and Y. Now, a pre-log structure on a scheme X is a log structure if it satisfies, so we have this pre-log structure, and we require that the restriction of alpha to the preimage of the sheaf of invertible functions on X induces an isomorphism with OX star. So here this is the restriction of alpha. And okay, let's see right away in that setting what is the canonical log structure that we put on our scheme X. So we define, so in the setting here, where this strict normal crossing divisor, then we define the sheaf of monoids, so on every open U, and now it could be again either Littell or Zariski topology. We define this sheaf by taking good functions which are invertible outside D. And now this M gives a sheaf of monoids, which is a subsheaf of the structure sheaf of X, and which clearly contains OX star. So just the inclusion of M into OX is a log structure on X. And then some maybe less interesting examples are that if X is any scheme, we can consider the log scheme X OX star, and this is called the trivial structure on X. But we can also take the full OX as a sheaf of monoid, and this is called the empty log structure. And respectively, I mean, by the definition of a morphism of log structures, one can see that this is the initial object in the category of log structures over X, and this is the final object. So actually X goes to X.
It's the other way around, isn't it?
It's,
the trivial structure is actually the right adjoint in this case.
This one is the...
It's the right adjoint to the forgetful functor, not the left adjoint. It's the empty log structure is the left adjoint.
Yes. Yeah. So now maybe just to say it once that monoids are commutative semi-group with one, and morphisms of monoids maps 1 to 1. And so just the fact is that push out and pullbacks always exist in the category of monoids. But if you think about it, to describe this explicitly, in general requires some care. So if you really want to see a thorough discussion about this, you can have a look in August's book on logarithmic geometry. So just to give an example of what could happen, somehow some fact, if we take just the sum map here, then maybe, I mean, for example, considering the kernel of such a map is just 0, 0, but surely the map is not injective, so somehow it requires some care. And nevertheless, we can use push-outs. So if P is a submonoid of Q, we can take such push-out to be the quotient monoid. and this is how you deal with quotient, etc. So I won't insist much on these aspects, but apparently general monoids can be quite subtle. So now clearly we can consider the category of pre-log structures on scheme X, and the category of log structures on X, and clearly we have here the forgetful functor, and we will describe an adjoint to this. I am not saying in which direction I leave for you to figure out if it's left or right. But anyway, if M onto OX, if this is a pre-log structure on X, then we define the associated log structure as follows. So we take this diagram, take the preimage of the unit. This maps.
Can you make it a bit bigger?
Oh yes. Bigger or higher?
And clearer.
Bigger and not down there.
So we take the diagram. This maps to OXR via alpha. This is not necessarily an isomorphism because M is just a pre-log structure. This is inside M. And here we can form the push out. So this will give rise to a sheaf of monoids on X, which is MA, and it will have a map onto OX, which is just given by the universal property of this push out. And by construction, this alpha A will be a log structure. And this functor, which meant a pre-log structure M to this MA, will be the adjoint to the forgetful functor over there.
I think it's left adjoint.
Just to make sure, is a morphism of log structures a morphism of log schemes for which the underlying morphism is a scheme, or is the morphism of monoids, because the maps go the other way around?
Yeah, it's true. So, but I think it's just a convention in the end.
Sure, but it matters for this question.
Yeah. So
Whether it's
I would say actually it's a morphism of log schemes such that the underlying morphism is the identity.
So when earlier you said initial and final, it was for this.
Yeah, so it's
convention.
the
Okay.
other way around.
Yeah.
So, yeah, I don't know. Every time to think left or right, I should really write down the homomorphism and check where it goes.
I just want to know what a morphism of log
Yeah,
structures is.
Yeah, I would say that, but maybe some authors just define it as a morphism of sheaf of monoids which commutes with the two maps there. Right? So I don't know actually which one is most appropriate. So then some more basic constructions we can do are as follows. If we have two schemes and the morphism of schemes, we have direct images and inverse images of log structures and the pre-log structures, and we'll commute with this. So, for example, if M is a log structure or a pre-log structure, analogous, we have a problem in figure out like this on X, Then we define the direct image log structure. So I decorate with log to distinguish from just the push forward of shifts. And this will be a log structure of y, and this constructed as follows. So I take here, this is just the push forward of the shift n. This will come with the map to f star OX. Then the morphism of schemes gives a map in this direction. And we define, so we can consider here the pullback, the pullback of this diagram. And then this will have a map into OY, and we define f star log n to be the log structure associated to this pre-log structure. On the other hand, if n is a log structure of y, then we can take the inverse image as a sheaf induced by n, and this will map into f minus 1 of OY, and the map of schemes gives then a map into OX. Now this is a pre-log structure, and we define the inverse image of n to be the log structure on X associated. But once I lift it, you will see it.
Yeah, but the manipulation lasted only for a few seconds.
Associated to.
Very, very small.
Ah, yeah.
Be patient. You just have to hold it for a moment. Turn it and hold it.
No, you may have to reset it.
Yeah, you may have to press a button.
It's
Where is the-
Just hold it.
The-
It's fine.
where the red light is.
Ah,
Red
okay,
light.
okay.
Oh, no, no, no.
Which one do I want? Ah, this. Okay. And yes, so actually I want to choose that. So now actually these functors are also adjoints from log structures on X and log structures on Y. And we actually have the following, that if n is a log structure on X and then is a log structure on Y, we have that the morphisms in the category of log structures on X from the inverse image onto n. So yeah, so now I actually
Now your
think
convention
that
is
I
the other
want
one.
this to be just a monoid.
Yeah.
So I changed my mind. And this is isomorphic to the homomorphism inside log structures on Y from n onto the direct image of n. And both these sets will be in bijection with the extensions of F. So recall that F was a given morphism of schemes from X to Y. Extension of F to a morphism of log schemes from X with the log structure M to Y with the log structure N. Yeah, so this means that F star is left adjoint to F star, I think. No?
In that category.
Yeah, yeah. So now an important example.
Bigger.
Example. You can write capital letters then. Anyway, so P is any monoid. And assume we have a homomorphism of monoids. So again, always with multiplication into the global sections of some scheme. Then to give such homomorphism is equivalent to give morphism of sheaves of monoids. So I will denote with P underline X, the constant sheaf of monoids on X. And to give such a morphism is the same as giving morphism of sheaves of monoids from Px onto OX. So this is a pre-log structure. And taking the associated log structure, we get that every morphism of monoids will induce a log structure on X. And let me give you another description of this log structure. That if P is a monoid, we can actually consider this ring. So this is just given by finite linear combinations in the elements of P with the obvious operations. And we can then form an affine variety, an affine scheme. And the canonical map, so we have a map, an obvious map from P into ZP, which by this, in this way, will induce a log structure on ZP. So this space has a canonical log structure, and we will sometimes write P onto spec ZP to denote this scheme with this log structure. And now we know that if I have given a morphism of monoids into the global sections of the structure sheaf of some scheme X, then this automatically extends to a morphism of rings. And we know that to give such a morphism of ring is the same as giving a morphism of schemes from X to the affine scheme. Spec Z. And then the log structure on X induced by this morphism of monoids via this procedure coincide with the pre-image of the canonical log structure under this morphism. Now to further expand on this, actually we have the following. That so we can consider the set of morphisms of log schemes from x m, so x m is just a log scheme, onto that log scheme for some monoid p. And we have a natural map from this into the morphism of monoids from P onto the global section. And this map, this is a bijection. Yeah, the map is just taking global site induced by the. So we have the map of sheaves, and then we from the. Okay, I'm right. So by definition, to have a morphism of log schemes means that in particular we have a map from the pre-image of this, and this, recall, it was just the constant sheaf on ZP. This was inducing the log structure here. And we have a map from this onto N. And then actually this is just the constant sheaf. Oh, sorry, P. That P. Then pulling this back as a sheaf gives only the constant sheaf stock P on X. And then if we take global sections, we indeed get the global sections of these are P. So we indeed get a morphism of monoids. Okay, so let's see how to see this is a bijection. It's quite easy. So if we start now with a morphism of monoids, then we can compose it. This is the map induced by global sections by the log structure here, and we have already seen that to give a map of morphism from P onto the global sections of OX is the same as giving a morphism of schemes. So we get a morphism of schemes onto this affine scheme. And so this is what we need to define the morphism of log schemes. Because now this will be the underlying scheme morphism, and by construction, this morphism will be then will induce a morphism from the constant sheaf with stock P into this morphism of sheaves, and then such thing will this is the morphism induced here, and it will commute by construction. So here actually I define the morphism of pre-log structure, but then I should take the associated log structure and I get my morphism of log schemes. So now I need to define a couple more things on monoids. So if P is a monoid, then there is a universal abelian group with a map from P into it. So to define the groupification of P to be just in which we invert all elements basically. So we just write symbols P prime with P prime and P, and we declare two such things to be equivalent. If exists another element of P such that we have P1 prime, P2, P equal to P, P2 prime.
Someone says primes are similar to ones.
Yes, it is.
Okay, to change slightly. You're right, it was a bad, it was a bad choice. So let's take P and Q. And now I declare, but it's just the usual, so P minus 1 Q will be the same as P minus 1 1. Okay. Just give me a second. Such that. And now P2 Q1 P Q2 Q1. Okay, the usual thing.
Yes.
And so we have a map P into P group, and every morphine from monoids from P into an abelian group will factor over this map. And then we define a monoid is said to be integral if the cancellation law holds. So AB equal AC implies B equals C. And equivalently, this you can easily check that this is equivalent to the standard map P into P group is injective. And then we say also that P is saturated if the following property holds. So if A is an element of the groupification such that for some n, A to the n belongs to the image of P into the groupification. So if this happens, this implies that A already belongs to this image.
Just to check, so the if and only if in the definition of integral is an equivalent condition, and in the definition of saturated, the implication sign is part of the.
No, yes.
Part of the.
Yes, so that's the condition.
So yeah.
Okay, so maybe equivalent.
Yeah.
So this is just part of the condition. So if I take A in the groupification such that for some power stays in this image, then it actually already comes from there. And then finally we say that a monoid is Fs if it is finitely generated integral and saturated. And so probably the one of the main properties of why restricting to such monoids is that if first of all, if P is any monoid, we have P star in P are the units, and we can consider the monoid P bar defined as P mod the units. And now if P is Fs, this implies that the groupification of this quotient So this is called sometimes the characteristic of P, maybe, I don't know. So, I think. And so this is actually a free abelian group and finitely generated. So I think at least this is how I explain to myself that's one of the main reasons why we care.
So can you give an easy example of a non-saturated monoid?
Yes, so like so if we take n, all numbers bigger than something.
N zero, so
Now,
so n minus one does it, right?
Yes.
yeah,
Yes.
yeah, right. Also in Z, I can take the monoid generated by 2 or whatever, and this is not going to be. Oh no, actually this is.
No. You take the natural numbers starting at 0 but omitting 1.
Yes.
0, 2, 3, 4, 5.
Hmm.
Yeah.
Yeah, that works.
So then, unification is set.
The groupification is Z, and 2 is there, so you should have also 1.
Yes, the one
Yeah.
is there.
Thank you. Okay.
The one is here.
So now we want to define a more restricted class of log schemes, which are then called FS log schemes.
Can you say what FS stands for?
Yeah, fine and saturated. So usually fine was
The conjunction of finitely generated and integral is fine.
yes, and so F stands for fine, and then I add saturated. So chart. So if x n is a log scheme, a chart for n is a morphism of log schemes. Onto one of these fine log schemes, such that the pre-image log structure coincides with n. So if I take f minus 1 px and then I take the associated log structure, this is isomorphic to n. No x, p spec zp. This is necessarily small. Okay.
Sorry, what did you write?
I wrote that if so. Okay, let me get.
No, don't.
So first I put here another definition, and they say that xn into yn is strict if f upper star of n is isomorphic to n. So here a chart is such a morphism that is strict. So in other words, we have seen that such a morphism is the same as giving a map from P into X M. And we want that once we take the associated log structure given by this map, then it's isomorphic to M. And now we can define Fs log scheme. So Fs log scheme, which again stands for fine and saturated, is a log scheme which locally, and now again either étale or Zariski, depends which one we're working with, admits a chart sub with P and Fs small. No, there is for FS log schemes and x is at any point. We can take as a chart so around x. We can take a chart with p equal m, so this will be little x and bar. So let me explain this. Yeah, so this m bar is in this setting is the unit of mx are exactly x star. It's a log structure, and yeah. Now we have the following. So since my monoid is fine and saturated, then all these are inclusions into the groupification because these are integral. And I know that this is just a free abelian group. So such sequence can be split, and such a splitting will induce this splitting as well. Just defining the image of m bar, the image of these intersected n. And
With n, same as n x.
yes, I can do this actually. Yeah, I can do this as monoids or sheaf, but in my application I take this to be at the level of scope. And
Sorry, why does the splitting restrict to a splitting?
because these are all injectives inside here. I mean, these monoids are contained in the groupification.
Yes. Maybe I'm stupid, but I don't.
It's also not clear to me.
Maybe we're both.
Yeah, that's very likely.
Why do you land in?
You say, why do you land in here, right?
Yeah.
Mm.
I mean,
But
if
because this should split this sequence, so it can't.
if m is the natural numbers, and m bar is also the natural numbers, then, and then, oh no, so that doesn't work. Then sorry. I mean,
You could somehow, yeah.
it's probably true, but
Yeah, not sure whether. I mean, I don't have an example where it doesn't split, because it doesn't mean it splits. I think.
Because of the fine and saturated?
Yeah, this.
Yeah, this.
The map to the group is injected?
Yeah, I mean, and then actually also. I mean, this gets the direct product there. Yeah, okay, so, I mean, what I was going to say is that if this splits, then we get the map from this onto, yeah, we get the map from this onto mx, which by assumption maps to oxx. And then this is going to necessarily give our chart. But if it doesn't split,
no, but it should. It seems very plausible, right? Because
yeah, I think, I mean, if it doesn't, I mean, yeah.
You start on the top right, you map down, you choose a lift, you choose another lift, they differ by number to the unit.
Yeah, exactly.
Yeah.
The space. Yeah.
So does it work or?
Yeah.
I think so, yeah. I think so.
Yeah, so maybe I shouldn't express my conclusion nicely, but we can find the chart with that because just giving that map, that there should be a little X over there. Okay, so for example, let me give some examples. So if we take for X just the spectrum of a field, so 1 point, and then if we work with Zariski log structures, then every sheaf on X is constant. So a log structure is just a monoid with a map onto K. Now I wanted to draw the same diagram over there to get a splitting of m bar plus k star. And then the map actually from m bar plus k star to k just maps couple to, so it's the projection here if m is the identity, otherwise it's 0. And this is because k star is actually the preimage of the units here, and therefore everything else should be mapped to 0. And to see now here, I mean, in the étale case, it's actually not only just a monoid, but we have to consider also the Galois action. And so, for example, so we have, we can say that the sheaf on this spec K in this setting is just, the log structure is just given by this monoid plus the Galois action, and then there's no reason why such sequence should split with respect, I mean, why such sequence should split as a sequence of Galois representations. So, I mean, étale log structure are more complicated than Zariski one. So yeah, actually, I mean, to get this splitting, I'm assuming that it is an FS log structure. And another example is if R, if let's say that in the situation where D is a strict normal crossing divisor into a regular scheme, this gives rise to FS log structure. So recall that M was just the subsheaf of X of functions invertible outside D. So if X is not in D, then I mean the log structure is trivial, and for we can take a chart with P equal 1, for example. And if X is in D, then the local ring is a regular local ring that there is such a maximal regular sequence, and D is then given by the equation now around such point the log structure, a chart can be given by just and the free monoid, if you want. And this maps this couple, this tuple, to this. So this is a chart of the log structure around X, and MK is clearly an FS monoid. So this log structure is FS. Now I don't have much time left, but I want to talk about log regularity. So,
Sorry, can I
yes?
just to make sure I understand?
Yes.
So the pullback of something Fs is Fs? Or the pullback of an Fs log structure is again an Fs log structure? Is that correct?
Yes, yes. Because you can find the charts are locally given by some constant sheaf of monoids, and then when you pull it back, you get a constant sheaf with the same star.